All right, so for today's topic, we're going to be discussing the idea and the point of implicit differentiation. So usually when you differentiate, you have something that looks like this. You have f of x equals blah, 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 and all you've got over here are x and some constants. So times, plus, divide, whatever's going on, you've got f of x and then x on the other side. And so taking the derivative is really straightforward. I just say, okay, cool, f prime of x equals whatever the derivative is. And so that's very straightforward. The problem is sometimes you cannot get just f of x equals blah, blah, blah. For example, say if we had x cubed plus y squared equals 7, just as an example. The problem with this is watch what happens when we try to solve for y. Remember that y is f of x, at least for Calc 1. So this would be dy dx. What happens here is that I would get y squared equals, if I subtract x cubed, I'd have 7 minus x cubed, and then I'd have to take the square root. But when I take the square root, I get plus and minus. I have two functions, not just one. Remember that anything that's like squared like this isn't even a function because it doesn't pass the vertical line test. So at best, I'd have to split this off into two separate things and do each of their derivatives, but then how would I reconcile and put those things together? That's the question. And that's what implicit differentiation can solve for you. So say, to go back to the symbolic way of writing this, we had something like x times f of x plus, some other function of x, maybe squared equals 1 or something like that. Well, what we could do is we could just take the derivative of both sides. Take the derivative of this side with respect to x, and take the derivative of this side with respect to x. And then just go from there and see what happens. Well, what would happen here? Here I've got a product, so I'd have to use product rule. So the derivative of the first times the second plus the derivative of the second times the first. So I'll write that out. This would be the derivative of x times f of x plus x times the derivative of f of x. Then over here, I just take the derivative of this guy, f squared of x. Of course, the derivative of 1 is just 0. So then over here, derivative of x, that's just 1. And then I've got f of x. Everything's cool. Plus x times, f prime of x. Plus, this is chain rule, so 2 times f of x times f prime of x equals 0. And so now notice here, what I have is I've got some f primes. I can maybe put them together and factor them out, move stuff over. And then that's about as good as I can do for this. So let's look at this example that I had up here, the x cubed plus y squared equals 7. If I implicitly differentiate this, then I'm doing d dx, x cubed plus y squared equals 7. And so I'd have the derivative of the left-hand side equals the derivative of the right-hand side. And so then what I would have to do is just do the derivative of x cubed plus the derivative of y squared equals 0. X cubed is just your plain old derivative, so this would be 3x squared. But now when I do this, remember y is itself a function of x. So what I'd have to do is I would do chain rule, so I would do 2y times the derivative of y with respect to x, and that equals 0. And then I would just have to solve this for dy dx. So dy dx, if I subtract this over and then divide, would be equal to negative 3x squared over 2y. And sometimes you might be able to make some sort of substitution to get rid of the y, but not all the time. And so this would be the implicit differentiation of that. So again, I used a couple examples here, one a little more concrete, one a little more abstract, to try to drill in that the point of implicit differentiation is sometimes you can't solve for just f of x or just y. And if that happens, you just have to do implicit differentiation. And when you do that, you might have some y's left over in your answer, and that's acceptable. That can happen. So that is a couple examples illustrating the point of implicit differentiation.